So in terms of an agenda, we will start by briefly recapping the subjects covered in the last 5 webinars, just to get an understanding of where we're sitting. So today we are going to be looking at our selection software on the project side of things, which is HySelect. And the purpose of this 6th webinar in the series is to bring together everything we've learned in the last 6 months or so, and bring it into a single package and a project package to be able to put everything together in a nice manner, and take all of these calculations, run these calculations on balancing, on control valve sizing, control circuits into our HySelect software. And it's not, this webinar today is not a webinar on training you how to use it. It's more a case of showing you how the software operates, so that if there is any requirement for it in your region, please feel free to reach out and we can maybe arrange a more in-depth training call. But this is also the sort of material that you could get from the likes of our engineering centre, if you have that sort of need on your projects. I'm going to start with a brief introduction to the software. We're then going to delve into running a calculation example on a small project I've got, that we're going to go through and run all the calculations and get a result at the end. We're then going to look at something which is relatively, I would say, a little bit slightly more less known in the HySelect software, which is a really nice feature called search and replace, which is going to allow us to actually optimize the design in a few clicks, compare different solutions, how they compare in terms of the valve work within them and the end system result. And then, yeah, that's kind of it for today. So let's start with a little bit of a recap on what we covered in the previous sessions. So the very first 2 sessions back, I think they were back in maybe October or November last year from memory, we talked all about balancing. And with balancing, we were talking about adjusting design flows to terminal units under design conditions when all of my control valves are fully open. And we looked at ways and means we could do this while creating minimum of additional pressure drops. And we saw the reason for balancing to make sure that we had fundamentally enough flow to the right areas of the system, and really, really importantly, doing it whilst adding in as minimum of additional pressure losses to the system as possible to ensure we were optimizing our pumps. And on the back of that, we also covered how to optimize with dynamic balancing devices, and we covered a couple of our key balancing methodologies with our TA scope. HySelect in particular, what we'll cover today, really helps with these methods because it gives me a basis. It builds up a network that I can then use to upload to my TA scope and run some of these self-balancing techniques, the TA wireless and TA diagnostic technique we looked at. And so we're going to cover today how we design systems to be balanced and how HySelect can do that and enable that. We then moved on in, I think this was the 3rd of the webinar series, to look at how differential pressure actually varies during use in a system. And we learned that the half load on a system, so when we design our system for a cooling system, we're designing it for, say, 35 degrees outdoor temperatures. We don't see those temperatures very often at all. For the vast majority of my cooling season, we're running at around about half load or below. And that is considerable. That's a considerable fraction of our time. Somewhere in the region of kind of 70% of my cooling system, depending on exactly where we are geographically, is going to be spent at about 50% of load. And that 50% of load only accounts for 20% of flow in the system. So we design a system for full duty, for full flow. We size our pipes, we size our pumps, we size all of our balancing valves for this. And 70+% of the time, we're at only 20% of the flow. And one of the reasons this really matters is because of something called the inverse square law, which is something I introduced right back at the start of the webinar series, and that's the relation between differential pressure and flow in a system. And at 20% of flow, because my differential pressure in any device, so in a full system, is directly proportional to the square of the flow, we have this relationship where that means only 4% of the total pressure losses in the system we've designed to are there for 70% of the year. And where do they go? Well, if we have a pump running constant head, we are still emitting that design head, that 100 kilopascals, 150 kilopascals, whatever that design pump head needs to be to satisfy my full load. But we have some dynamic devices in the system. And in a basic system, those are the control valves, because these are the devices that are moving to change the load in the system. We're controlling my temperature throughout the system, or controlling my heat HVAC temperatures with these control valves. And what can then happen is we effectively apply that pump head almost entirely on the control valves themselves, which is going to mean we're going to have a large influx of differential pressure on my control valves, and that's going to distort the control we may have in my system. We then moved on to look at the control circuits in a bit more detail. And how do we deal with this big variation in pressure? And we introduced something called the circuit characteristic. And the circuit characteristic is what we were defining as the relationship between the input to my control, being my input from my controller, my 0 to 10, my 4 to 20 milliamps, whatever my control signal I'm using, and the output from the system, being the power we're emitting into the room, the amount of cooling power we are providing into that space. And there were a few components that made that up. We had my terminal characteristic, which is my relationship between flow and power emission of my terminal. This is generally what we call an overlinear characteristic, because my differential temperature across my terminal is going to increase as I reduce the flow. We also introduced the valve characteristic, and you'll note this almost matches and opposes this characteristic here. And the reason for that is, if we think of my valve, the input to the valve is a 0 to 10 volt signal. That 0 to 10 volt signal is controlling the lift of a standard control valve. And therefore, we want to have the lift being directly proportional to the opening, which is going to control my power, or control my flow, which is going to control then the power. We introduced then something really important called the authority of a control valve. And the authority of control valve is how this differential pressure is building up on the control valve as the flow starts to reduce. As we said, only 4% of the pressure drops in the system are apparent at low load, at half load and below. So my differential pressure is building up on the control valves as they're shutting, and we need to ensure our design has dealt with that effectively to gain a good level of control. The final piece of the puzzle is my actuator characteristic. This is my input signal versus my lift. And the global target is this nice linear global characteristic. And that linear global characteristic is going to lend itself to a really easy control. If I need 10% more cooling, I give 10% more input, 20% more, 20% more, so on and so forth. That's going to make the control side of things much more stable and much easier to control. We want to do that from a mechanical design perspective, because otherwise the electronical side of the control algorithms are going to have to be extremely complicated and varying depending on where we are in a system. And as we're going to learn tonight, this morning, should I say, for you, we're going to be looking at how, when we design systems in HySelect, how it's going to select products for us effectively to ensure we have this good level of authority. And you may remember we talked about an authority range of being 0.25 as a minimum up to a design maximum of 0.5. We could go beyond that, but in essence what we are then doing is applying more differential pressure in the system with limited output and limited gains in terms of improvement of control. So that's the purpose of balancing, the purposes of sizing of controls and looking at control authority. And we're going to kind of try and bring that all together a little bit with HySelect. And I want to start with an introduction to what HySelect actually is. In a more general sense, from calculating a hydronic system and sizing of it, there's three related areas of development on the balancing control side of things. We can look at differential pressure control, our differential pressure controllers for dynamic balancing, terminal unit valves, so valves that are on my terminals and are controlling the terminal, are balancing my devices, and finally balancing and control valves, separate devices for doing balancing and control. And the idea is each of these products, and we'll see in a slide, when we're sizing them in a system, a selection of one is going to influence the selection of another. So if we were doing them all as an isolated component, we're going to need to know a huge raft of information to size that correctly. And HySelect is going to enable to do that as quickly and as easy as possible. And the idea is to size them optimally together in the context of their differential pressure to ensure we have the absolute optimum selection for my valves and how they operate within a system. And the idea is this systems approach is transforming a set of different valves into a complete and consistent hydronic solution. We are not just selecting a number of valves. We're selecting a full solution that is going to operate as efficiently as we can. And we want to do it in the most commercially sensitive way as well. We don't want to be providing more products than we need because we're going to have a more expensive system that's not going to have any gains in terms of operation. If I take, for example, this circuit here, where we've got a cut of a circuit, and we wanted to look at, for example, sizing this control valve. If I wanted to size this control valve, I would need to know a number of things. I'd need to know what is the differential pressure in my terminal, what's the differential pressure in all of the pipework sections being served within here, what is the set point of my differential pressure controller. The same if we looked at this valve here. We need to know differential pressures in terminals, pipework resistance, resistance between different sections of the pipe. We look at sizing a balancing valve. We need to know what's the control valve pressure drop, what's the set point of my differential pressure controller, what are the pipework resistances, again, what's the terminal unit resistance to size my differential pressure controllers, like this here. We need to know all of this information on differential pressure of the components within the circuit so we can calculate the correct setting for controlling differential pressure. We also need to know some external factors. What is the differential pressure variation externally to the circuit to ensure we select a product that is appropriate for the differential pressure variations you're going to see. And you can see very, very quickly, if you want to size and select a system correctly, we need to know a huge amount of information just to size one or two products in that system. And the idea with HySelect is to bring all of these different parameters together into a maximum output, minimum input type scenario. And we do HySelect, there's a few different options within there. We can do individual selection across all of our category ranges. So be that thermostatic control, balancing control, as we're going to be looking at tonight, or pressurization. If we want to just say, okay, I would like to select a 2-port control valve for a flow rate of, 1 litre a second, and the differential pressure needs to be 20 kilopascals. So if we got all of that information from a design produced elsewhere, we could do that. The most important section of the piece we're going to be looking at today is this hydronic circuit calculation mode. And as I said, that's based on a minimum data input to maximize a calculation output. And that's this little cut we're seeing here. So for example, we can use it to size an injection circuit. To size an injection circuit, we need to know a myriad of information. What's the flow? What's the differential pressure? What's the power? What's the pipe lengths? And HySelect is going to allow me to do that whilst providing a minimum of information in. Really importantly as well, it has a dynamic update function. If I change a parameter, for example, if I size my system with a known set of pipework sizing, and I go back and say, actually, no, I want to change my pipe sizing parameters. I don't want to size to 200 pascals a meter. I want to go for some slightly smaller pipes. I'm going to go up to 400 pascals a meter. I don't need to completely redo my calculation. I can just change those parameters, and HySelect will update my selections and my sizing accordingly. We can upload and download data to or from the TA scope. We can take a system we have built on the computer with HySelect, upload that data to the TA scope, go and set all my valves that will have all the recommended minimum settings, all the pre-settings being calculated, run a say TA diagnostic balancing procedure on this complete project, save those measurements in TA scope, download the data back from the TA scope, and you have a full balancing report on your computer. You can then export to PDF, export to Excel, and share that with the project teams. Also has some unique features, such as calculating authority of two-way valves and three-way valves. So we can take that bit of additional work away, and it will automatically calculate and resize for that. We can look at how do we optimize pump head. It can recommend the minimum pump size we need, and how do we optimize that. We can even do, we might have some time to look at this. I haven't planned it, but we may still have time depending on, is planning a diversity factor. If we're working on a particularly large system where we actually don't want to size the plant and the pumps to the full load, we want a diversified load on there, we can add in a diversity factor across different areas of the system. So that's kind of an intro and an overview of some of the things we can carry out. But as I said, what I want to spend most of this webinar looking at is the plant calculation mode itself. And I'm going to have a look at project mode in HySelect. And I have here a relatively small system, not a massive system, but by no means a small system, with a number of different devices on there. And what we're going to do in the next sort of 10-15 minutes or so is carry out the selection for all of these systems on there. And to do that, we need some minimum information. And the information we're going to start at the end and work our way back. We need to know what is the duty of each of these devices. Now, the great thing with HySelect is it doesn't need to know the flow rate. If you give it the power being emitted by the device, the differential temperature across it, it will then calculate your flow. We can also use it to calculate from a set of factory figures on a pressure drop on a coil. What is the actual pressure drop at design conditions? Or simply, we could just be given the design calculated flow and design differential pressure of the unit. And in here, we've got, as you can see, a 1, 2, 3, 4 branches of fan coils and 1 branches of air handling units. So fairly typical, as you may see in a sort of mid-sized project you might be working in with fan coils and this sort of thing. And what we're going to do is we're going to break this down, and we're going to calculate it piece by piece and go through and see just how relatively quickly I can build this system, and then what we can look at in terms of some of the design data we get out of there, and how we can optimize that system and ensure we are using it and we're sizing things in a correct manner to optimize my system design. Now, there's one key piece of missing information that we don't currently have on screen that's also really, really important for HySelect, and that is the pipework distance. Because the majority of differential pressure losses within a HVAC system are in the piping network, we need to know what is the piping lengths in each of my circuits to enable us to be able to correctly size and select the valves. Because to select a balancing valve appropriately, we need to know how much differential pressure it needs to remove. So therefore, we need to know what is the imbalance at design conditions to size that valve. If I want to size a control valve, I need to know what are the differential pressure variations on that control valve so I can ensure to size for a good authority. Without that pipework information, I'd be working blind. So relatively speaking, if you think of it from a drawing perspective, this is kind of like a hybrid between a schematic type drawing and a layout. Getting the layout drawing to have the pipework lengths and the schematic type drawing to show me a nice, easy, simplified layout there. And to size that, how do we size the balancing valves? How do we size the balancing control valves? How do we size the pump? How do we size the control valves? All of this sort of information. And what we're going to do is we're going to break it down into sections. And we looked at this during the balancing part at the start of this series on how we break these systems down into modules. And we're going to split it, and we're going to start with our first module. And this is the thing that sometimes looks a bit strange when we're doing a selection, is we're going to start with this module here. So what I'm going to do is I'm going to now open HySelect, and I'm going to show you how we can, oh, whoops, wrong one, how we can now break this into a system. So in HySelect, we have my project calculation mode, and we're just going to call this ANZ example. and I want to set, oh, whoops, I can't spell, for example. And I want to set this as a cooling project. And I'm going to say that there is currently no additive in there. So a cooling project, fairly typical cooling temperature, 6 degrees supply temperature with a differential temperature of 6 Kelvin. And I'm going to start by adding in this pump system here. So we're going to start at the start. And what we're going to do is we're going to right click on here and we're going to add a circuit. And my only options now are to add either a distribution circuit. This could be a secondary circuit running off a somewhere that's already pumped and we just need to, there's no pump, or in our case, it's a pump circuit. So in that case, we have no control. We're using manual balancing and we have our pump. So we're going to just simply press next. And at this point, anywhere we can add in information is shown in purple. At the moment, if we'd already selected a pump, if we knew what the pump head, if we'd done some preliminary calculations, we could add in the pump head. For now, we're going to just leave this as blank. And we're going to add that circuit. And what I've now done is I have added in, I have to press cancel to come out of that. I've added in this first section here. And I now want to move to this next piece. And this next piece is going to be the distribution pipe from the pump to my first circuit and this first balancing valve, this first module off my main system. So if I come back into HySelect, I'm going to right click on here. I'm going to go add circuit within here. And in this case, there's no terminal unit. Again, it is no control and it's a manually balanced circuit. And we're going to go next. And again, we have a little bit of information we've got to put in. The difference here now is we need to also put in the length of the pipework, and that is the length of the distribution from the pump. So looking back at my drawing, if I would flash it up, but unfortunately you will miss, it won't allow me. There is 4, 5, 7 meters pipework. So that means in total 14, because we have 7 meters in the flow and 7 meters in the return, 14 meters of pipework from the pump to this first circuit. And we can then press add. And we've now added in this first circuit here with a balancing valve. And you'll notice at the moment we've got no flow, no differential pressure. The only information we really have is the pipework length in this first circuit. And there's a reason for that. HySelect works so that it calculates the flow in each of my devices and then accumulates that up to size the upstream devices. So what I'm going to start with now is we're going to go into this circuit, we're going to go within this circuit, and we're going to add this very first circuit here. This very first circuit here, which is the first fan coil unit off here. And in this case, it is 8 meters from my 8 meters of distribution to this circuit. And you'll notice there's 3 meters within the circuit itself. And we've got this information of my power and differential pressure. So if I come back to HySelect, I'm going to go back in and I'm going to go to add a circuit here. And this time we are going to choose a terminal unit because this is now the fan coil and the associated circuit off it. It is a proportional control. And for this example, we are using what's called adjustable and measurable control valves. So these here, and you'll notice we get 2 options for the circuit. For those of you that tuned into the webinar where we looked at control circuits, for two-way control, we talked about two-way direct circuits and two-way injection. The drawing shows it as a two-way direct circuit. So we're going to select this guy here. And you'll notice now there's a lot more areas, a lot more bits of purple we can add some information. So I'm going to start by adding the pipework length. So the distribution from my main balancing valve to here was 8 meters. So that means there's a total of 16. And within my circuit, there was 3 meters. So there's a total of 6 meters within my circuit itself. Next, we need to add the flow rate. Within the system, on the previous one, we weren't given a flow rate, but what we were given is a power and a differential temperature. We were told This was a 2.8 kilowatt fan coil running at a differential temperature of 6 Kelvin, which is now calculated at needing 402 litres per hour. We were also given a differential pressure, but the differential pressure was not a design value. It was a reference value at a different flow rate. And my reference flow rate was 500 litres an hour. And my reference differential pressure was 19 kilopascals. And you'll see now what HySelect has done is it has selected the required pipe, selected the pipe size, select based on this flow rate, which comes from here, this differential pressure, and it's carried out a pressure drop calculation of my pipe work in all areas. And we can now add that circuit. So what we've now done, we've added this circuit here. And we now actually have 1, 2, 3, 4, 5, 6, 7 identical circuits, each with 10-meter distance between them and 3 meters within the circuit. So I could go back into HySelect and we could now go, okay, we want to change this up to 7. All other parts are the same, apart from here. Instead of being 16 meters, this is going to become 20 meters because we said there was 8 meters from the first circuit and 10 meters in between all the rest. And with one click, I can press add. And what I've now done is I've added all 8 circuits in. We've sized my balancing valve. Here, we've sized all of the two-way control valves. So we can see we have my two-way control valves here have all been sized with my minimum design authority calculated. We've got my balancing valve here has been sized. We've sized all of the pipe work in the distribution, also included for pressure losses for T's, because HySelect knows if you need to tee off a pipe, you're going to need a T, and in your end connection, you're going to need an elbow. It knows all of this from how you connect pipe together. It's going to include these accessories as well. It's calculated, selected all of my actuators. Everything has been done in, as I say, I've been talking through this, going through at a relatively sedate pace, and you can see very quickly we've selected quite a large number of devices. Now I want to move on to this next circuit. And the first circuit here is 18 meters away, and there are 5 meters between them. So we're now going to go into A. We're going to add a circuit. This time, again, it is a no terminal unit here, no control. We're going to go next. We want to add it in location 2. And we were, if I look back at the drawing, apologize, I have it on my other screen, but you'll have to believe me. It was 3 meters away, so 6 meters total of pipe work. And we can then add that first circuit in. And you'll see at the moment, there's no flow rates written. There's no sizing of pipe. It's just sized. Let's just take a random size from there. And we're going to go to add that in there. And we'll come back in. We'll go back into here and we're going to add a circuit. So what we're now going to do is we are going to add in this air handling unit. So in this case, we are again running proportional control with manual balancing and standard two-way control. So we have more options on the two-way control, but we have a standard two-way control circuit. So I'm going to go next. And we have the same sort of setup as we had before, where we need to add in our key information. And we're told on my drawing, we're 18 meters. So we're now, that means 36 meters of pipe total from the distribution, 5 meters distance between the distribution pipe and the device. So there's 10 meters of total in there. And this time we were given a flow rate, and the flow rate was 5,000 liters an hour. And the differential pressure was 40 kilopascals. And you'll see now, it has now selected my balancing valve, my control valve, my actuator. The keen-eyed among you may notice it's selected one with a low authority. We'll talk about that when we get through the rest of this solution. So we're now going to do this. We're going to add this in. And we're going to add that first circuit. And in the case of here, we now have another 1, 2, 3, 4 circuits that are all going to be the same. They're all going to be 10 meters apart this time, so 20 meters. And every other part of that circuit is the same. And we're going to add to 4 here. If we come back out, we've now added my 5 air handling unit valves. And we've got all of that data populated and sized for these valves as well. The keen-eyed of you among you may have noticed this last one was actually a 3-way valve. So you're going to say to me, Rob, you've got it wrong. But very easily, I can go into this valve. I can edit it. I can come back a step. And I can select this 3-way dividing circuit like we have here, which is what's shown on the drawing. Go to next. And it's now going to reselect all of this information before, and it's now reselected that as a 3-way control valve on the end. So we've now carried out the selections for this bottom row of fan coils and all of my air handling units. Next up, we have 3 fan coil circuits. And you'll notice, for this example, we've kept it really simple. The duty for each fan coil is the same. The distance between each fan coil and the next one is the same. The only slight difference is this circuit and this circuit only have 7 and the others have 8. So I can make my life really quite easy. I can come in, I can copy this circuit. I can then paste it in A. We now have this. Again, paste it in A. Finally, paste it in A. So I've now copied, I now have all 5 circuits in there. And all I simply need to do is a little bit of amendment to add in to change a few of the things that need to change. So things that need to change is circuit number 3 and circuit number 5 only have 7 fan coils. So I can just go into here. So circuit number 3, I can go to this 8th one and I can, and I can delete it. I can go into circuit number 5 and I can delete the 8th circuit. I now have 3 and 5 with only 7 fan coils. And the other difference is the distance from here. So we have 10 meters between circuit number 2 and circuit number 3. So we can go into HySelect again. We can go to edit here. And this was now 10 meters, so 20 meters total. Carried out that, we've changed it. And then if we look, there's 3 meters between 3 and 4 and 3 meters between 4 and 5. So we can go back into HySelect. I can then edit this. So this becomes 6. And again, edit this. And this too becomes 6. And in a relatively short space of time, by my watch, that was in about 10 minutes or so, we've completely built all of my circuits. And we have sized the total flow we need for the whole system, the total delivered power to the whole system, the supply and the return temperatures, the minimum pump head we need. And we've selected and sized all of the balancing valves, all of the control valves within that circuit, or within that whole system, in a really quite a short space of time. And if I look in my results here, when it loads, we've even got this lovely article list showing you all of the products, all of the selections, a more detailed list on the sizing parameters of them, the balancing valves we need, even a pipe list of what pipes you need to buy. And now let's have a look back into the project and let's have a look at some of the intricacies of this. So if you can remember from when we looked at the original, when we looked at control valve sizing, we recommended a minimum control valve authority of 0.25. That's my minimum. That's what's actually defined in HySelect as well. So you'll notice that actually at the moment, most of my control valves are effectively oversized because the authority is too low. And this is something to look out for with HySelect. And you might say to me, well, hang on there, Rob, that's a you problem. HySelect selected these. But we have to remember with HySelect, it's selecting to a range of parameters. And the parameters it's selecting to are actually these parameters we start with at the start here. So what it's first doing is it's sizing pipes based on these targets of target and maximum pressure drop. It may be those targets are wrong. At the moment, I'm not going to touch those. Actually, what's important at the moment is it's this thing here. It's how many sizes above and below. So I'm going to now click onto here and I'm going to increase how many we can go to below. And watch what happens. When we go to 3 sizes below, HySelect is now able, because it's sized a pipe, and in this case, it is sized a pipe for, if we go to the distribution, it is sized a, within the circuit, it is sized a DN50 pipe based on my parameters, but there is a requirement of a DN25 control valve to get the minimum authority I need to satisfy this system. So that's the reason we need to be a bit careful and have a look at a few things. And that's something to be aware of when we're looking at this. And now we've actually really sized. You'll also notice that, unfortunately, the minimum authority is still too low in these designs. So we're going to look at something a little bit further in a moment. But we've now sized them. We've got all of our balancing valves. And if we said that's acceptable, we're going to accept that because of what we've got and what we need to do. We've got all of my differential pressures calculated. It's calculated the pressure loss required in each of my valves. The design authority is calculated, if we expand here, what the pre-setting needs to be for each of my valves, what the differential pressure is going to be in each of my valves, what the minimum pressure drop is in there. It's even going to show me where my index circuit is, so what is the least favored circuit totally in the system, and we can click into there and it's going to show me which is the least favored, which is the last circuit in here. And it's carried out all of this lovely bits of selection. And relatively quickly, we've kind of selected this whole pipe. And in reality, what have we selected? We've selected 35 or calculated 35 fan coils and air handling units, 75 segments of pipes, 70 T's, 80 elbows, 5 modulating control valves, 12 balancing valves, 32 VCMs, which is one of our balancing control products, and a pump. So a total of 308 components we've sized, we've selected in really short period of time. But as we noticed, we haven't necessarily optimized the design. And the final thing I want to look at today is actually how we can optimize with something called search and replace. So the search and replace tool allows users to very quickly update things such as pipes, control circuits, distribution modules, temperature regimes. And what we're going to look at today is 2 things. We're going to look at pipes because that's quite an interesting one. You may have noticed I have selected this based on steel pipes, but it may be you decide you want to change your design and see how it compares in plastic or in copper. And what this is really useful for is efficiently comparing different solutions we can have here in a few clicks. So, whoops, let's go back. I've gone too far here. Come on. Now let's have a look. So let's pop into HySelect itself. And I want to now look at what's called the search and replace function here. go away. And we'll look at the search and replace function. And we have options. We can do temperatures, pipe series, hydraulic circuits, and what I'm interested in for this purpose is hydraulic circuit, should I say. And I want to apply it to the whole project. And what I'm going to do is I want to have a look at, if you remember when we talked about increasing authority, we could do that in a number of ways. We could downsize our control valves, or alternatively, we could add in differential pressure control. Differential pressure control means we are minimizing the variation in differential pressure to within the circuit we're controlling only. So I actually only want to apply this to my modules. So my modules being each of these modules. And what that means, I'm going to change my manually balanced modules on my distribution circuits to be differential pressure control. And I would like to change the circuit to be a distribution circuit. And we want to change my balancing to be differential pressure control. So going from manual balancing to differential pressure control. And if I press start, it should hopefully find this is what we currently have. And this is what we want to change it to here. And we can go apply to all. And it's now found, hopefully, 5 circuits. And it's now updated these 5 circuits to include differential pressure control on each of my circuits. It's automatically sized and selected these valves. And why is that really important? If I now go back into them, you'll notice I no longer have an authority below 0.25. I have improved the control valve authority on all of these circuits. I have optimized my system. I have ensured, by the case of, in this case, just adding in 5 differential pressure controllers, I've optimized this circuit. And to do that, it was only a couple of clicks. So for example, if I wanted to do some work on a circuit, I say, okay, this is designed as it's my initial stage design. I've just gone for manually balanced everywhere, but I've noticed I have some issues around my control valve authority in some cases. And I want to price up, or I want to change the design to include these. And I can just compare and contrast from a commercial perspective, from a technical perspective, with just a couple of clicks with this search and replace function. So very, very quickly, I've now been able to size my DPCVs. And in this case, adding in 5 differential pressure controllers has improved the controllability of my circuit in total in just a couple of clicks. The next thing I want to quickly show before we go is, before we open for the questions, is actually looking at pipes. So the other option is to do pipe series. So I could say again, for the whole project, I want to replace, for example, my steel pipe with, I don't know, let's say we wanted to try some, what have we got? Let's go for some table X copper, good old copper. And we want to replace it all with copper. We're going to start, we pay replace all. And it's now updated all of my pipework, updated my sizing, updated my pressure losses to include, for now, if we go into it, here we go, copper pipes. And I could have said, I will actually only want to apply that to part of my circuit. I don't want to apply it to all of it. I could have selected the bits I wanted to change, a bit I wanted to update. And very quickly, I can run these selections. It's selected everything, optimize my system in a pretty straightforward manner. And the beauty of this is we can build this within the Hydronic system with the software. We can design the circuit, we can build the circuit, we can upload that circuit to our TA scope, we can carry out my balance. We've been given all of the pre-settings required for each of my valves. We can see, if we go to balancing valves here, the required preset for every valve. I can preset all of my circuits to make sure my balance is as close to possible before I go in. I can then reduce the amount of time I need to be on site balancing because I'm pretty close to the start. I can carry out that balancing exercise, and then I can re-upload that data back to HySelect and present it based upon my set figures. What are the actual set points? What's the areas? And it's a really nice, brought together kind of holistic, everything in one place with HySelect. For me, this is one of the kind of most important parts of what we do as a company. HySelect. It's one of I would say the underutilized parts. Generally, a lot of times it's, can we have a selection for a PICV, a control valve? Yes, you can. To do it properly, we need to know lots of information, and you can get a much better system out of it to do it that way. So that's kind of it on the demonstration for today. Just wanted to do a quick advertisement. If you are in Melbourne in May, I will be over in Australia and New Zealand in late April, early May, and we're going to be with one of our distribution partners, Hydroflow. We are going to be at the ARBS exhibition. So if you are planning to attend and you want to come and talk to us, we're going to be on stand 323. I should also be doing, I think, 2 sort of presentation sessions around data centers, and also presenting a hospital case study where we did some really nice work on optimizing the air handling units in a hospital. So if you are around, you are there, it'd be really good. Pop by and say hello. But that's the end of this series of webinars. Thank you very much to everybody that's tuned in. I hope you found it useful information. And if you have any questions in the meantime, please do not hesitate to reach out. And if I could just ask one thing before we go to the Q&As, if you could take a little scan of that QR code in your middle of your screen there, it should take you to a quick questionnaire of, I think it's around 10 questions maybe, just around how you thought the webinar went today, any further training you might want to receive. And it's really, really useful for us as a team to sort of track what we've been doing, check we're training in the right areas. But for now, that is all from me. I will now check into the Q&As if we've got any questions coming at all. And whilst I do that, let me also allow people to unmute themselves. Okay, so somebody has asked, balance system with all the control valves open sometimes is a challenge as diversity has been supplied when selecting the pump. Is there a method to address this type of commissioning for a project? Yes. It's also something I would generally recommend that is done from a design perspective as well. If we go back, it's probably quite easy. Actually, quite a nice way to look at it is if I go back into this system here, for example. So the idea is so this is a question around where we're applying the diversity. So the first question would be is how is that diversity being applied? Is it within a circuit or is it circuits in general? What I would generally recommend doing is to correctly commission a system with diversity applied, realistically it needs to be have at least some form of differential pressure control included. So in the example of this circuit where we have 5 distinct differential pressure control modules, we would balance each module with that module being the only one online and using the differential pressure controller. We can then set the differential pressure controllers to achieve design flow with all of those units open. And then what you would then do is close a number of circuits, as in branches. So for example, if you said, well, for my diversity, my pump has only been sized for, I don't know, let's say it was a 50% diversity for the sake of argument, really big diversity. You would close sort of probably in this case 2 of the branches, prove that you can still get flow in the 3 that remain open, open those 2, close another 2, and then prove again. And then at that point, you've proven you can get flow and get the correct design flow to all units within a circuit, and proven that the pump is capable of applying the right amount of being able to keep up with the right amount of things in the project. It gets a lot more difficult if you're wanting to do diversity within a circuit. So say, I don't know, 5 valves are open of 10 within a circuit, 5 control valves of 10 are open. because at that point you realistically need to have some form of differential pressure control somewhere else on the system to try and to do that diversity, because you're kind of sizing it to a lower flow rate. But it's certainly things you can look at, and a design is very useful to sort of get that from the initial design stage. But in fact, I can show now, for example, how to add the diversity factor here. And choosing the level of the diversity factor. So to do that slider control, so choose where we want to apply it. So let's say we want to apply diversity to all of these circuits. Let's say we don't want to apply diversity to the air handling unit circuit, and the diversity is 0.5. And what we've now done is HySelect has now crashed. No, it's not. It has now applied a diversity across the number of valves. And if you go back, it's applied this diversity factor to resize my pipe work based on only having 50% load. So the way it bases it is having 50% of the valves open on there. But because you really need to still prove every valve can get 100%, because the diversity is applied to every valve getting 100%, it's quite difficult to do staging at an opening. I'll always recommend doing it at a branch level, because it makes your job a bit easier that way. So hopefully now, now pass unmute themselves. Have I done that? That worked? Yes, perfect. So if there is any other questions, you should now be able to unmute yourself if you need to. But I can't see. Let me just double check. There's nothing in the chat at all. No, I can't see any further questions here or in the chat. But thank you very much for joining this 6th and final webinar. If there's no further questions, I will leave everybody to get on with their day. Say thank you very much. Hope you found this series useful. We will be hopefully releasing a new series of webinars in the next, I suspect probably to start in probably June. So probably sort of midwinter for you, start of the summer for me. That we'll be releasing the series of what we're going to be covering in those ones in the next month or so, I suspect. But that's all from me. So once again, thank you very much for joining, and I hope you enjoy the rest of your day and the rest of your week.